Other than the test, I'll go over the test again at the end of the class. But if anybody is in Monday's lab, double check your enrollment, because a few people got dropped for not showing up at Monday's lab who may have been coming to Tuesday or Thursday's lab instead. Just FYI. So I only heard from one person, but I just wanted to bring that up. So if anybody is in Monday's lab, just double check and make sure that you're still enrolled in the class. I don't think it'll appeal. I don't think it's going to be a problem for anybody, but I just wanted to double check. Okay? We had to certify rosters last week, and the instructor for Monday's lab based his certification on people who had actually come to Monday's lab. So if you are enrolled in Monday's lab but haven't shown up there, but are still here every morning and maybe coming to Tuesday or Thursday, you need to look into that. All right, so let's start talking about air and water, or weather and climate. Air and water. I've titled this two different things. We're talking about weather and climate, and obviously this week's lab is the Climate Summit, so we're going to come back and talk a little bit more detail about that in lab. In fact, I'll go into the actual discussion about climate change in lab. We'll talk about climate today, this morning, but climate change we'll talk about in lab. And there's a lot of interesting perspectives to take on that, and that's why we do the assignment the way we do. So let's get started, though, with the basics of weather. And then climate is weather over time, so we'll do that at the end. Weather is based on two things, really. If you think about how all of our weather is generated, it's based on the presence of water on the surface of the Earth and in the Earth's atmosphere, and heat from the sun. So heat from the sun warms the water on the Earth's atmosphere and drives it through a water cycle. And most of the weather that we experience is part of that water cycle. Water is an interesting compound because it has many special properties. It's one of the few compounds, one of the few things that is actually in all three states of matter on the surface of the planet within the same temperature range. Now, everything has a temperature at which it freezes. Most of the things we feel are solid can be turned into liquids if you heat them up enough, and even into gases. Iron can be a gas. Inside big stars, iron is a gas, right? So if you heat it up enough, even iron can become a gas. All three phases are possible for any compound. But it's very rare to see all three phases of a compound within a narrow temperature range as we do with water. So within 100 degrees Celsius, from 0 to 100 degrees Celsius, we see water frozen, liquid, and as a gas. Water vapor in the atmosphere is different from mist, which is condensed water, which is just sort of spread out, a vapor. So we'll talk a little bit about that as we go through the water cycle, and we'll look at that in a second. But I wanted to talk a little bit more about water special properties before we do, because one of the reasons water is so special is that it's found in all three states on the Earth's surface, but also these other properties. The fact that it's polar. It has two hydrogens bonded to an oxygen at an angle. And we'll talk more about covalent bonds later. We'll talk much more about heat, energy later in the course. But those angles of those bonds move the electrons of the hydrogens to one region, one side of the oxygen, and essentially expose the protons of the oxygen a little bit on the other side. So you get two poles with charge, a positive and a negative pole of a water molecule. And because of that, water is able to take any salt, any ionically bonded compound, and separate those ions in solution. It's the universal solvent because of that. So you put salt in water and it dissolves. You put any salt in water, right? Epsom salts. You know, there's a lot of actual salts. Salts is actually just a general term for any ionically bonded cation and anion combination. And when you put those into solution of water, they separate. That's unique. That's what makes the ocean salty, and so on. Water also has, because of this polarity, they sort of stick together. The water molecules line up according to this polarity, and it produces surface tension on the surface of the water. So when you push on the surface of water, it pushes back a little bit more than most liquids do. In fact, you've seen insects or even the lizards that can run along the surface of the water because of that surface tension. You've probably also noticed adhesion, which is a similar property as water is being drawn up a straw. If you look closely, it's got that curved surface to it because it's literally sticking to the sides of the straw, and then gravity is sort of pulling it down in the center. That's called adhesion. And that's also why water forms droplets. Most liquids, if you spilled them on a surface, just flow into a puddle. Water tends to form droplets, and that in itself is unique. All of these things, along with its particularly dense state as a liquid. If anyone's done a belly flop, you know how dense water is. It's hard to get through it. You push on it, it pushes back. It's actually incompressible, which is how hydraulics work. If you push on it, hold that pressure. There's a lot of force being exerted by the water that when you release can do a lot of work. So again, we'll talk a lot more about work later, but obviously when you lift a car off the ground so you can change the oil or work on the car, using a hydraulic system works because when you put the liquid under pressure, true hydraulic fluids are no longer water, but that's what it's based on. When you push on the water, it pushes back. It can push back quite a bit. We'll talk more about buoyancy too. Obviously, when you displace water, it pushes back with an equal force. But right now we're talking more about water in the atmosphere, so I'll move beyond this to one more thing, and that's the specific heat capacity of water. How much heat can water hold? And it can hold a lot of heat energy. And we're in the hurricane season right now. So we'll come back and talk a little bit about this later this morning because we're looking at the heat that has been absorbed by the oceans over the summer starting to move back into the atmosphere as the atmosphere starts to cool down. We just got a nice cool front, right? It's cooled things down a little bit. Well, that cooler atmosphere now will absorb the heat from the oceans. The heat will move from the oceans into the atmosphere, and it can move fairly rapidly, and as the Earth spins, can lead to cyclones, to hurricanes. So we've seen a few tropical storms already, a few hurricanes, undoubtedly see a few more throughout the rest of this season. And we'll talk a little bit more about how those get driven, but it's because water can hold more heat than the air and can hold it longer. But let's take a little bit closer look at the simple water cycle. Actually, I guess should have had this up while I was talking about that. But let's take a quick look at the water cycle. And again, I bring this one up because it has a couple features that aren't always included that are important to me as an earth scientist. That has to do with infiltration into groundwater and surface runoff and the erosion that is driven by that. Remember, we've talked with the rock cycle, and we've talked a lot about weathering and erosion and water as a weathering agent. Well, that's all part of this. It's just not usually discussed as part of this. It's separate, but I wanted to point that out. What we are worried about right now, however, is the fact that evaporation of water from the surface, either from the surface of lakes and streams or from transpiration off of leaves or any other water that's lying around. We have a good rain and you see evaporation coming off the concrete. All that evaporation is putting water vapor into the air, water in its gaseous state. Now again, you might wonder if the point at which water turns from a liquid into a gas is 100 degrees Celsius, how do we get all this evaporation on days where it's only 95 or 85, which is Fahrenheit, which means it's only 30-something Celsius, right? It has to do with it's per molecule that temperature that amount of energy has to be reached. So again, we'll come back to that when we talk about heat energy, but that's an obvious question that I at least want to address. There's enough energy from the sun to bring molecules to that point and cause evaporation. Plants also allow that to happen more readily by moving the water up to the leaves and intentionally having the water evaporate off the leaves to draw more water up the plants. That water vapor near the surface is warm. As it rises up in the air, what's called adiabatic cooling occurs, and the water vapor cannot stay in that state, and it condenses into droplets. That forms clouds. We'll look at various types of clouds. Yes, last night was an interesting evening because my daughter and I were driving around and we noticed various types of clouds in the sky. And we'll look at some of those. It's unusual, but two completely different levels of clouds at the same time. But however they form, and we'll talk about low clouds, medium, high clouds, they can then become dense enough for that water to become too heavy to be held up by the air, and it falls as precipitation. It could be rain, snow, sleet, freezing rain, hail, whatever. Now we're used to rain. We don't get a lot of freezing rain or sleet or hail here. Occasionally we get some of that. We hardly ever, and occasionally we'll get some snow. So we'll talk a little bit about each of those. That precipitation, of course, doesn't just fall on mountaintops. It falls anywhere. But if it falls on high ground, it then runs off to lower ground. And so we've talked about watersheds and all the water that falls into a watershed that collects into a river or stream. So again, all of this ties together. We'll come back and talk a little bit more about groundwater as well, because that's an important source of water. And we've already talked about it a little bit. But let's look at the atmosphere and water in the atmosphere for a second. When we look at the layers of the atmosphere, I'm going to go ahead and go to this next slide, because we can see we live in what's called the troposphere, down here, near the surface. And the height of this can vary a little bit, but this is typically about 10 miles from the ground to the top of the troposphere. This is the atmosphere we live and breathe. The atmosphere that is generally warmed by the sun. There is an ozone layer between the lower stratosphere, or in the lower part of the stratosphere, that protects us from the sun's ultraviolet light. And then the stratosphere continues for about another 10 to 31 miles up into the sky. So it's pretty, these are not drawn to scale, or else that would be up to three times as thick as the troposphere. If you've been in an airplane, you've been up close to the stratosphere, or perhaps into the stratosphere, but you have to think about something here. I mean, there's a couple reasons why you would want to get that high to fly, but there's a couple reasons why you wouldn't want to go much higher. The plane is being held up by the air below it, but it has to move forward through the air, which provides resistance. If you get up through the troposphere into the lower stratosphere, there's less resistance because the air is less dense, but there's also less to keep you up. You have to move faster to stay up there. So you can only stay that high if you're moving really fast. Again, we'll talk a little bit more about that when we get to heat, because I'll throw in some how buoyancy but also thermodynamics work on planes. Above the stratosphere, there are some other layers, and again, you can see somewhat different diagrams, because sometimes they'll put an ionosphere in here, which is actually part of the thermosphere, but it's sometimes shown as a separate layer, and it discusses that here. The mesosphere, and again, as you get up, what's interesting is we've got, near the surface, the atmosphere is being heated, not only by the sun's radiation coming in, but by the Earth's radiation going back up. And how that heat gets trapped in the troposphere, creating a greenhouse effect. As you get above that, as you go up in the atmosphere, it cools down because the air molecules are farther apart. And so it gets pretty cold when you get up into the stratosphere. But if you were to measure the temperature of the air molecules in the thermosphere, it would be very low. But if you measured the actual amount of energy in a molecule, a single molecule, it would be very high, because the sun's radiation is hitting those molecules and making them move around very fast. There's just very few of them, so they don't run into each other very often. This is sort of foreshadowing a lesson we're going to learn about heat, in that what we measure, thermal energy, which is heat, measured as in temperature, is actually just looking at the kinetic energy of those molecules. It's not actually looking at the amount of thermal energy. So we'll come back to that. But these are the layers of the atmosphere. We'll spend most of our time talking about the troposphere, of course, because that's where we live and breathe. That's where most of the clouds form. Some very tall cumulonimbus clouds can reach into the stratosphere, but for the most part, they don't get that tall. Matter of fact, most cumulus clouds form low. Their base is low. We then see stratus clouds and various types of stratus, all the way up to altostratus, that can form from low to sort of mid-level clouds. We see cumulus clouds here most of the time. Those accumulate during an afternoon, oftentimes, and you might get a shower from those. They don't last very long. They'll form and then they'll move on, or they'll rain out. Stratus, however, can fill the sky. So when you get rain for a day or two at a time, those are usually stratus clouds, and you'll notice they're very flat. They're a little bit higher than the cumulus clouds. Last night and this time of year, we're starting to see some cirrus clouds. And these form at very high altitudes. If we lived in an area where we expected snow, we would see those and go, oh, it's going to snow. Because that's what that's where snow typically comes from, though we'd never get enough of that type of cloud typically to produce snow. And of course there's everything in between. There's every combination. We saw a lot of cirrocumulus last night, for instance, and altocumulus and altostratus. We didn't see any true stratus clouds, but we saw plenty of cumulus clouds as well. So I mean, there were a lot of different cloud types in the sky last night. It was very unusual. And we'll see most of these at some time or another in Houston. But the bottom line is, these are water, right? They really are fog. If you've walked through the fog, or you've driven through the fog, you've driven through a cloud, or walked through a cloud. It's just a cloud that's formed on the ground surface instead of up in the atmosphere. And so it really is water droplets dispersed in the air and being held up by the air. Those water droplets can fall. Depending on the temperature of the air they're falling through, you get different types of precipitation. Now, this is using elevation as a way of showing a change in the air that the precipitation is actually falling through. So as you get closer to the cold air, you get more likely to get snow because it's actually falling through cold air, and so it's frozen. Whereas in any of these others, it may start out in cold air and as frozen, but by the time it reaches the ground, it's thawed into rain. Now, not all precipitation starts as snow and then turns into rain, but this just to illustrate why we have such a variety of precipitation. You can get freezing rain or sleet. There's a little bit of a difference there. Freezing rain is snow that's melting as it falls, then it hits cold air and freezes when it hits the ground. Sleet is falling as freezing rain as it falls. So a little bit difference there, but they sort of feel the same if you're in them. And again, we get mostly rain, but we do get a variety. All right, let me move on. I've been concentrating on water right now, but we have to concentrate on one other thing. And I said heat was the other ingredient. But the reason heat is an ingredient in weather is because of what it does to our atmosphere, to the air. And it turns the air into different densities depending on whether the air mass is getting a lot of heat energy from the sun or whether it's getting less heat energy from the sun. And of course, if the air is holding a lot of water, it's more dense. If it's got less water, it's less dense. So this density of air has a lot to do with our weather. We can basically talk about 4 types of air masses. And then we can talk about these air masses moving around on the surface of the Earth in various ways and running into each other. Where an air mass meets are called fronts. Let me just bring up this diagram to talk a little bit about the 4 types of air masses that we might see forming. The M here stands for maritime, meaning over an ocean. The T for tropical, the P for polar. So these are very general classifications. If the air is forming over a warm ocean, closer to the tropics, it's going to be warm and moist, right? But if it's forming over the ocean near the polar regions, it's going to be cold and moist. It's going to have less moisture. It could still have moisture because it's over the ocean, but it's going to be colder air, and so you're going to get a cold moist. If it's forming over a continent, you can get continental tropical air, which is going to be dry, hot air. Think about a desert. And if you get air forming over an air mass over land mass in the polar regions, you get cold, dry air. Now, let's think about our own weather patterns just for a second, because we've got the 2 main forces here. And this is showing fronts, 2 cold fronts. These are the blue lines with the little arrows on them, indicating that this cold air is moving south. As the cold air moves south towards us, it's going to run into this warm, moist air. That's going to create weather, because that warm, moist air is less dense than the cold, dry air. The cold, dry air acts as a wedge to push the warm, moist air up. And as I've already said, as that air rises, it cools down. It can't hold all the moisture. The moisture falls as rain. So we typically get rain along these fronts. That's where most of our, like, quote, weather occurs. This confrontation between the cold, dry air and the warm, moist air can occur anywhere as these air masses move around, and they quite typically occur right over us, and we get a lot of rain from that kind of thing. Because we're close to where this warm, moist air can come off the Gulf, and the cold, dry air can come down with a cold front like we just had come through the last few days, or this last weekend. And this is just a better picture, a little bit of what's going on here. If you've got the cold, dry air, the warm, moist air running into each other, they create a front. There's going to be a pretty, depending on how strong the front is, and let me make one, when you hear about a cold front, that's relative, okay? We get cold fronts in the summer, and they take our temperature from 98 to 94. So it doesn't really feel cold, right? It's not cold air, but it's colder than what was here before. And that's all that matters. Any difference can create a front. We're talking about air masses that are forming in different regions of the world and then being pushed around. And we'll look at how they get pushed around in a minute. But as they get pushed around, they run into each other. If it's a really distinct difference, then we can get storms and tornadoes and really dramatic weather. If it's less distinct, then they'll sort of start mixing together a little bit more, and we'll get extended rain sometimes. And we see different types of these patterns throughout the year. We tend to see the really dramatic differences early winter and early spring, but these can happen at different times of the year. So we would draw this, and I'll show you a weather map in a little bit, where we use these lines to sort of show what the fronts are. This one also shows what's a warm front, because the warm air is moving towards the cooler air above it. And so we would draw that as a red line with circles instead of triangles. But they're pointing in the direction that the air is moving. So when you look at this, you can tell what direction the air is moving and what air mass is dominating in that front. So here's or the other thing that I need to bring up about these different air masses. I've been using the word density, and I want to translate that into another word that results from that, and it's called pressure. Now, this air mass is sitting on the Earth, right? Literally pushing on the Earth and exerting a pressure on the Earth. The denser the air, the more it weighs, the greater the pressure. Right? And it's quite literally, the denser the air, the more molecules of air we have, the more molecules of water vapor we have. And it literally pushes on the ground surface with more force than if it were more spread out, warmer, and the air molecules move apart. So air density results in different pressures on the Earth. We can draw lines where the pressure is equal. And what this allows us to do is essentially see where the air masses are. Because a center of low pressure is a warm air mass. A center of high pressure is a cold air mass. And this is oddly sort of opposite of what we would typically see. High pressure, though, keep in mind, is cold air. Cold air is denser. It pushes on the Earth with greater force, creating higher pressure. If you follow a hurricane, for instance, I can only explain this, maybe these are some winter storms up here creating these low pressure, because what you get with a storm is the air being pushed up out of the way, cold air coming in, pushing the warm air up very rapidly, creating sort of a vacuum. And that's very low pressure. And so the eye of a hurricane has extremely low pressure, and the air spins around it to try to sort of fill that space in as quickly as possible. This is how we generate weather maps. So let's take a quick look at a weather map. The way these are generated, there are weather stations all over the place. Matter of fact, if you have WeatherBug on your phone, if you have that app, you're basically tying into a weather station that is either here on campus, because we have our own WeatherBug station here at UHD, or maybe some other elementary school around town, or some other a library, wherever they have these. These WeatherBug stations are all over the place. And so you can get one that's right by your house and literally get the measurements, weather based on these measurements, really close by. Every one of those weather stations are measuring a variety of things at any given time. And they can put them into this weather arrow. this weather arrow shows us the information. And I could show you a weather map from the National Oceanographic and Atmospheric Association, or a couple other sites that put weather services, for the newscasts and things, that take every one of these arrows and put them on a map, and then use those to draw those isobars and put these values on there, and that's how they identify the air masses and how strong they are, and how quickly they're moving, and which one is expected to get somewhere when, and what weather that could cause. So all that information is in this arrow. This tells us, for instance, at this particular state, that it's mostly cloudy. About 3/4 of the sky is filled with clouds, 75%. The pressure is 196, which is actually 1019.6 millibars, but you'll see it abbreviated in this way on a weather arrow because meteorologists all know that if that's a 0 or a 1, then it's 1,000 something. If it is a 9, sometimes it does drop below 1,000, and so you'd see a 9, or in a really low pressure inside a hurricane, you might see an 8. But usually it's 9 something to 1,000 something millibars of pressure. Millibars is the best unit of measurement for this because it gives us a fine resolution, but we could talk about atmospheres of pressure or millimeters of mercury. There's a lot of different ways of measuring pressure. On this arrow, not all arrows, but this one is more complete, and it shows you what the change in pressure has been over the past 3 hours, and that's really the most important thing. Now, when you're running these in real time, you can have computers keep track of this. But this is, in other words, the pressure has risen, it's gone up in the last 3 hours. That means cold air is coming in, the pressure is going up, so cold air is moving in. There's been about a 1/4 inch of precipitation in the last 6 hours. The wind is coming from the southeast at about 15 knots. A long tail is 10 knots, a short one is 5. A knot is close to a mile per hour, so 15 miles per hour or so. That's pretty good wind, pretty strong wind. The temperature currently is 28 degrees Fahrenheit. So as I said, there's cold air, right? That's pretty high pressure, pretty cold air, pretty high pressure. Pressure's going up. And then it's showing a visibility of about half a mile with some snowfall, the little symbol there for snow. The dew point, this is the other key measurement, and it doesn't surprise me that there's some precipitation because the dew point is pretty close to the same as the actual temperature. The dew point is the temperature at which water vapor condenses into precipitation. This occurs almost every morning as the atmosphere cools down. The sun is on the other side of the earth, so the atmosphere is losing heat, it's cooling down. It cools down to the dew point just before sunrise usually, and we get dew on the ground. It's precipitation just very close to the ground. If on some days where that lasts for a little while, you have fog. Fog is 100% humidity, which occurs when the ground temperature is at the dew point. Typically here in Houston, we would see a dew point. We might see a temperature of 90 with a dew point of 72. So we don't get precipitation until nighttime as the temperature gets down that low. But as the humidity comes up, as the atmosphere absorbs more and more water vapor, that dew point comes up with it. And so as the dew point gets closer to the actual temperature, we get more likely to have rain. And that does occur. So all this information is here. It's really, and these are degrees Fahrenheit, not Celsius, so it really is a cold day here. If those were degrees Celsius, it would be, in the 80s. It'd be a little bit warmer. This is the result of mapping all of those weather arrows onto a single map of the United States. Now, also keep in mind, you can see these isobars, they essentially are circles. They have to be circles. It only makes sense for them to be circles. They're like contour intervals of the atmosphere. Right? If you do a topographic map and you have a contour line, a line of equal elevation around a hill, it can't be broken, or else there's a break in space. It just can't happen. Same thing in the atmosphere. These lines have to come together into circles, but that's not always going to happen in a small map like this. It's going to happen globally, and so we'll just see the edges of some of these coming in on the west and going off to the east. But within the United States, we can see these isobars that are defining, again, a low pressure system here, a high pressure system down here, and again, a little bit backwards of what we would typically see. But we can also then find where that pressure change is occurring and draw the lines there that indicate where our fronts are. So we do see a cold front coming down from the northeast and slightly from the northwest, but we have some warm air trapped in between them in the Midwest, or in the sort of Midwestern states here. This kind of weather system, we would expect to see quite a bit of, perhaps, some precipitation up there. Down here, this high pressure means we've got probably clear skies. Again, high pressure means the air is cold and dense. It's not holding a lot of moisture. We typically get our clear blue sky days on high pressure days. Low pressure days are when the warm air is being pushed up, condensing into clouds, and we tend to get precipitation on low pressure days. So you can get a lot of information from these weather stations, or from these weather maps. Again, there are various services that provide this information. I just use this slide to sort of show you it's something that we tend to take for granted, but it shouldn't be taken for granted. We are currently at a state where many of our weather satellites are becoming obsolete, and we are not replacing them. And so our ability to predict the weather is actually declining right now because we don't have the instruments available to do it as well as we should. Is that a big deal? Is that a big problem? Should taxpayers worry? Perhaps, if you're concerned about accurate hurricane tracking and accurate prediction and things like that. Now, let me also point out, if you're trying to predict the weather for Houston, it's impossible. Now, it's not impossible for a particular neighborhood of Houston, but Houston is a very large area, and we have 5 distinct weather zones in this area. So if you're trying to give a weather forecast for the entire area, it's just not possible. It's actually been measured how accurate weather forecasts are, and they're about 87% accurate across the country. But it doesn't always seem that way, because if you live in spring and you hear a 50% weather forecast and it's blue skies all day and not a drop of rain, you think, oh my goodness, they were way off. Of course, it rained in Sugar Land and half of the area got rain. So they were exactly right. 50% chance for the area means 50% of the area is going to get rain. It doesn't always mean you have a 50-50 chance where you are. So again, it's sort of like that healthy skepticism I started with. Just give them a little bit of a break there. You have to look at it in a little more detail. If you actually watch the weather, they do a pretty good job of showing you where the rain is likely to fall. But if you just watch the 30-second weather bullet, it's not going to be very accurate, because it can't be. All right. So my 2 cents for the poor weather meteorologists, weathermen and women who work in Houston. All right, let's get to climate now. The difference between weather and climate. We just talked about weather, and I could go on and talk about our weather patterns and where they come from, and I'll see a little bit of that in here, and I'll come back to that a little bit. But I want to focus on climate, because that's where we're going to go in our lab this week. Climate is weather over time. Any region tends to have a fairly stable pattern of weather over time. Now, we're seeing ours change, actually. In the 20 or so years I've been teaching this, our weather patterns have changed fairly dramatically. Whether that means anything or whether it's just a natural process or occurrence isn't clear, though we could look at some evidence and maybe try to decide. But for the most part, we can talk about climate at different levels, and if we think about it broadly, we can think about there being various types of climate zones, such as temperate climates, areas where you have 4 distinct seasons. You have winter, spring, summer, fall. Boreal climates, which are like tundras and taigas up in Alaska, where you sort of have 2 seasons, a warmer season and then a cold, extended season. Tropical climates really don't have much seasons at all, right? I mean, they don't really have seasons at all. It's always warm. Desert climates are a little bit different because they're controlled by monsoon, what's called a monsoon climate. We don't typically think of them that way, but what that means is you get a lot of rain for a short period of time, and then the rest of the time it's dry. So it's more about precipitation than it is about air temperatures. You can have cold deserts or warm deserts. They're both deserts. They just have little precipitation. The typical monsoon climate that we're used to thinking about, though, is in India, where you get 6 months of rain and 6 months without. So that's your obvious monsoon. And there are various forces that drive these different climate zones. And let me show you where these come from. It comes primarily from the sun's heating of the earth in an unequal distribution of heat. In other words, the earth is a sphere. It's tilted towards the sun a little bit. So when it's tilted towards the sun, the upper hemisphere gets more radiation, more direct radiation. When it's tilted away, the southern hemisphere gets more direct radiation. So you get summer in the south, winter in the north when it's tilted away, summer in the north, winter in the south when it's tilted towards. But no matter, that tilt is not enough to stop or to change the overall patterns of what are called prevailing winds in the jet streams. Those are a result of convection currents in the atmosphere because the sun's rays strike the equator with more directly and heat it more than it does the poles. The sun's rays strike the pole and glance off a little bit. So it heats the poles less than it does the equator. So you get hot air forming over the equator, cold air forming over the poles. Essentially, that cold air is going to sink and push the hot air up out of the way. As the hot air rises, the moisture accumulates into clouds and falls as rain. So the tropics aren't shown on here, but you have a zone called the tropics where most of that rain falls. Just beyond that, as this colder air starts to sink again, at about 30 degrees north and south is where most of the world's deserts are. Because that cold, dry air, it's cold relative to here, that dry air sinks and we get deserts. Now this isn't just from the poles to the equator, it's broken up into multiple cells all the way around the globe, but these are ongoing, they're always blowing. And so these winds on the bottom blow along the surface. These are called the prevailing winds. And sailors use these to get from one part of the world to another because they know the winds are going to blow them in that direction. Of course, now we have engines and things we can go against them. But before that, when it was sails, they had to go with the prevailing winds. The upper level of these convection cells are the jet stream. So you hear a lot about the jet stream. Keep in mind, these are all the way around the surface. So if we think, United States, in here somewhere, we're actually in Houston at about 28, 29 latitude, so we're pretty close to that line. So we've got prevailing winds that are typically blowing away, but also can shift. Our prevailing winds shift a little bit. They're blowing towards us in the summer as this moves down, blowing away from us offshore during the winter as this pushes us up into this range. The jet streams, again, are the opposite direction. So while the wind's blowing this way, the jet stream's coming at us this way. They're going this way, we're getting more of a jet stream from this. Anyway, so I could talk a lot about how this is driving all our weather because we have a time of the year where the air masses are being pushed from Mexico over top of us. And we have other times of the year, like now, where the jet stream's starting to push things from Alaska in the northern part of the state down towards us. They don't always stay very strongly defined air masses when they're coming in that direction, but we're just now starting to see where we will get more of those air masses reaching us. So those jet streams are always blowing at the upper levels, the prevailing winds are always blowing at the lower levels, and these are the winds that are moving the air masses around on the surface of the planet. And they move around in fairly steady patterns that allow us to define these different climate zones. The other thing that's moving heat around are the ocean currents, and I wish this was a little clearer, but we don't need the labels. We can see that a very similar distribution of heat is happening on the Earth. They're cold at the poles and warmer at the equator. And a little bit differently, though, than the atmosphere, it's the cold water that's sinking that is driving these ocean currents. You get very cold, salty water at the poles sinking, pushing its way towards the equator, which is pushing the warm air on the equator back towards the poles on the surface. Now, the Earth is spinning, and you may have noticed that those arrows on the prevailing winds were curved, not straight. And that's because as the Earth spins, the friction of the Earth's surface with the air and the water pulls the air and water along with it, but there's a little bit of a delay, there's a drag. So as the water is coming back towards the poles on the surface, it's being bent by the spinning of the Earth, the Coriolis effect. And so we see this warmer water coming from the equator towards us in the Gulf Stream, cooling eventually and coming back on the other side as colder water where it gets warmed up again. This is called a gyre. You notice a gyre in every ocean basin. If you've ever been swimming in California and wondered why it was so cold, this is why. You're on that other side of the gyre. So it's actually cold water coming down along the coast of California, and so that water's never hot. It's always pretty chilly. Likewise, our water in the Gulf is always pretty warm. It never gets really cold because we've got warm water breaking off the Gulf Stream coming into the Gulf of Mexico. And this Gulf Stream carries it on up along this way. Which is also why, if you look at the weather here, behind it, it's cold. Straight across, over here, it's warm. Because this warm water is coming over here and preventing the same weather pattern from occurring. So it explains a lot, right? We can explain all of this distribution of things by these patterns. The other thing we can explain by these patterns is the distribution of what are called biomes or ecosystems within these biomes. And again, they follow much of the same vocabulary. Temperate, where we get a lot of seasons, you get a lot of deciduous forests. Deserts, of course, desert climates produce desert ecosystems. Boreal climates produce tundras and taigas and things like that. The tropics produce rainforests because they get all that rain and are always warm. There are other types of rainforests than tropical rainforests. You get a lot of rain in the Pacific Northwest and you have a rainforest there. It's just not always warm. All right, so we'll come back a little bit to some of that. But that's sort of in a nutshell, weather and climate. Now we'll talk about climate change in lab, because as I've said, our weather patterns have been changing. Does that mean our climate is changing? Now let's develop that question a little bit more in lab this week. Let me reiterate what I said at the beginning for anyone who came in late, and then we'll do the quiz. The test is a week from today. There will be a 25-question multiple choice test that you will take in class without your books or anything else, right? It'll be taken from the book, though. So I'm going to go through the chapters of the book. I'm going to identify 25 questions. I'm not going to try to trick you. I'm going to be pretty straightforward, okay? But you will have to have read the book. The take-home portion will be 4 questions, each similar to the discussion board, where you'll be given an article to read or a video to watch or something like that, something to consider. It may just be my question directly. Or sometimes I even have you go online and play a game or something, and then you talk about it. Okay, so I want to see your thinking, your answers. That's open book. It's open anything. Open the computer, open your laptop, so to speak. You can talk to each other about before you write your answers, but you have to answer individually. Okay, I do want to encourage, again, any resource you can come up with your own response, but it has to be your response. If I see the same answer on more than one test, neither one will count. If I see an answer taken from a source, it won't count. I really want to see your words. Okay, so I'd rather see something that you struggle with a little bit than taking something authoritative from the internet and putting it on your test. Which, again, if you can find it, I can find it. So don't expect to get away with that. I'm not real strict. Again, I mean, if you show me that I'm not going to, just because you've got a sentence or two that I can tell came from somewhere else, I'm not going to automatically ding you. But if the whole thing does, then yeah, you're going to get less points. Does that make sense? Okay, so there's a 25 multiple choice questions in class, 4 take-home problems. You bring those back a week later. All right, let me get to the quiz.
What chapters was it?
Well, we're talking about basically the first 8 chapters.
Number 8.
Yeah, no, we don't get to. I can double check. Let me look at the topics and I'll show you because I know these are a little bit different than. All right, so 3 chapters in the introduction, and let's see, 10. Yeah, I guess it is. These aren't matching up. They didn't do the chapters the way I said to. So you're right, it's 10 actually. But it's these two units, Unit 1 and Unit 2. We'll do Chapter 10 on Thursday. In the syllabus I have it as Chapter 8, which what I didn't expect them to do is break the first unit up into 3 chapters. It should have just been 1 chapter. So if you take those out, it's if you treat the first unit as 1 chapter, which really it's supposed to be. But yeah, I don't want that to be confusing. It's the first two units. This test is on the first 2 units.
Thursday, right? Thursday. When is this?
It's a week from today, so next Tuesday. Now again, we'll talk about climate change in lab, so that's in the chapter as well, but we'll do that in lab. Okay, let's do the quiz. Number 1, an isobar is a line of equal temperature on a weather map. That's false. It's a line of equal pressure on the weather map. You can have an isotherm if you want. Temperature and pressure are closely related, right? We get high pressure because we have cold temperatures, but they're not exactly the same, so it can vary. An isobar is an area of equal pressure, so this one is false. Number 2, a front is the boundary between 2 air masses. True. That's true. And again, depending on the nature of these air masses and how strong the boundary is, we get a lot of weather, a lot of different kinds of weather produced. The troposphere is the layer of the Earth's atmosphere in which we live and breathe. True. That's true. The stratosphere above that, then the mesosphere, thermosphere, including the ionosphere. This one's true. Number 4, and this is one we haven't talked about yet, but we will in lab. These 3 terms may seem odd, but they'll make sense to you in a little bit. Obliquity, precession, and eccentricity are irregularities in the Earth's rotation and revolution around the sun. And that's true. Again, we're going to talk about these 3 things in lab. This has to do with the Earth's tilt and the shape of the Earth's orbit around the sun, and how differences in those characteristics can actually lead to the formation of glaciers or the retreat of glaciers over time. All right, number 5. The Coriolis effect is due to the Earth's revolution around the sun. That's false. It's due to its rotation on its axis. That creates the friction with the air and water. And it's interesting, keep in mind, the Earth is a solid object. The air is a gas. Oceans are liquids. And they're attached to each other only by gravity, right? The air is really a separate entity from the Earth, in a sense. Gravity keeps it close by, so they push on each other, and that creates friction. As the Earth spins, it drags the atmosphere with it. And that drag is called the Coriolis effect. Alrighty? So, false, true, true, true. Did I click the wrong thing? It's true on the last one too. I don't know why I clicked false. Oh, no, wait, it should be false. Oh, I clicked true?
Yeah.
Oh, I don't know why I clicked true. All right, so I messed up. But for you, it's false. It should be false. I said false, right? Yeah. All right. Well, I'm not going to grade myself. But it's all right. It's not going to hurt. It's the first time I've been waiting for that to happen, actually.
On chapter 2, there's two.